So if you do a scatter plot of data, like number 35 here, with fat and sodium, if we do a scatter plot and the data is spread out all over the place, first of all, if you had to describe it, okay, it's not strong. I wouldn't say it has any shape, okay. You couldn't really say if it's positive or negative.
There's probably like one outlier.
Might be an outlier here,
But I guess you can't really say.
but you
an
can't
outlier.
tell.
Yeah.
So, if you get a scatter plot that looks like this, with data points all over the place, it's not even worth finding the R value or finding the equation of the best fit line. Okay? So it's very important to look at the scatter plot first before you go to find an R value or the equation of the best fit line, if you will. Okay? Does that make sense to everybody? Because can the calculator still give you an R value? Can it still give you an equation of a best fit line?
Yes.
But why in the heck would we want it when there's no real relationship or association between the two? So very important to be able to look at the scatter plot before you go any further with any sort of question about its correlation or best fit line. Does that make sense?
Yes.
Okay, now look at the scatter plot for fat and calories. Okay, look at your scatter plot for fat and calories. If you entered it in a different list, you just got to change the Y part of your list on your stat plot. If you put the calories in L3, then just do stat plot L1, L3. Okay?
It's a little more linear.
What's this one? Calories?
Calories.
Got that one up?
Yeah, it's the right.
It's got calories.
The red one?
You're right.
Yeah. You have different colors and you have to like go to
Obviously, it's going to look different depending on the window you have opened up.
It's an L3, isn't it? Didn't you put this one in?
But hopefully, when you look at that scatter plot,
Just turn this one off. Turn this one on.
you see a little bit more of a linear relationship. Anybody still having problems getting their scatter plot up? What's going on?
I don't really know how to.
See if you can help each other out.
I don't really know how
So do you got you got that data entered?
Yeah.
Where are they?
There.
Stat, edit. So L1 is your X values and L3 is your Y values, right?
Yeah.
So go stat plot. Stat plot. It's above Y equals, right up here. Stat plot. Okay, plot 1. That's L1 and L2. Don't you want L1 and L3? So go down here to your Y. L3 is above the 3. Press enter. Press graph. There it is. You can adjust the window if you want it to make more sense though too. I mean, you got everything right here. You can maybe get your window down to fit better. You guys get it?
Yeah.
Okay.
We just have to. We just took out.
Make sure that you have.
Anybody else? You get it? Is it looking more linear?
Yeah.
Okay. So, you could agree that this does seem to have a little bit more of a linear relationship. Okay? If you had to describe it using the 4 things, how would your description go? Strong, positive, linear,
No outlier.
no outliers. Okay? A refresher. Strength. Looks fairly strong based on the graph we have now. Shape. Linear. Direction. Positive. Outliers. Doesn't look like it has any. Know those 4 things that you need in order to describe some sort of correlation.
What would another example of shape be?
Exponential, quadratic, all over the place.
So, would you say if it does look like exponential or something like that, could you be like strong exponential, or would you put weak and then put exponential?
I would call it a weak linear association.
Okay, and then just put exponential.
You could put, the shape looks more like it's exponential, you don't even need to use the word strong or weak as far as that goes, just give me the shape, the general shape. You could even put, if somebody doesn't know exponential, curved.
Okay.
So if
Okay.
it's not like, if it's not all on that line, it's gonna be weak, so if it was exponential, even if it was all closely like tight on exponential.
It would be a weak linear association. Could be a very strong exponential, but we're only worried about linear associations in this for right now. Okay? Everybody else good at those questions? Okay. Alright. Oh, also, I want you to put this down in your notes. So I'm testing it over. 3 things to check for in order to use correlation. Okay. We've kind of already talked about it just a little bit. The first thing to check to see whether or not it's worth getting an R value, check to see if it's linear or not. If it's not linear, don't even bother getting an R value. Okay, like the first one today. It was scattered all over the place, not even worth looking at its correlation. Okay? Second one, make sure it's quantitative. Okay? Make sure it's quantitative, not categorical. I mean, could you make a scatter plot using categories? Sure could, but you wouldn't want to find an R value for that. That wouldn't make any sense. Okay? And the third thing, again, outliers. Are there any and why are they there?
So I mentioned something in the book about like finding an R value with and without the outlier. Do you just take your outlier out of your
Take it out, find the R value, leave it in, find the R value, if there's a significant outlier there, yes. Yep. But on the quiz that we'll eventually have, okay, when I ask you what are the 3 things to check for in order to even use the R value or to discuss the correlation, these are the 3 things you want to check for. Then, if it looks like it's worth using, then you know the 4 ways to describe the correlation. So know the difference. 3 things to check for, and the 4 ways you describe a correlation. Okay, remember the 4 ways are strength, direction, form, which means shape, and outliers. Outliers falls into both of them. Okay? What's that? What's that? It's on the calendar. I have to check. Watch this video when I send it. Because there's a lot of good stuff in there. Okay. So, let's go ahead and, for this one, let's get our R value and let's get our equation of a best fit line. Okay? Go ahead. Stat, linear regression, L1, L3, or whatever your 2 lists were for fat and calories. Help me out. R.96.
Yeah. Best fit line would be y equals 11.81 x plus 210 211.
211, yeah. You said L1, comma L2, comma L3, like all those.
What is that thing on the
Find the best fit line, the linear model that represents the fat and calories. So whatever list you put your fat, comma, your calories in are the 2 lists you want to use to find your R value and your equation of your best fit line.
What's that thing on
It's a hat.
Y hat. Who's in the reading?
I'll talk about it exactly here specifically. Okay? Everybody got that? Everybody knows how to get that? Yes, no? Everybody good? Guys in the back? Yes? We're good on that? No, we're not? Okay, alright. So, what can we say about this then? For sure now.
It's pretty strong.
Pretty strong correlation, yeah, 0.96. I mean, the highest number you can get is what? 1. Alright, that's probably not realistic when you're collecting data. Not everything falls perfectly onto a line. So, that in itself is pretty good. Now, this right here, okay, is our linear model. It's our linear model. You probably saw that term in the text. Linear model. And it is the linear equation the calculator gives us that is the best fit line through the middle of all the data. So if you had to take that scatter plot and try to draw a line through the middle of all those data points, obviously you couldn't hit all of them, they're not all exactly on the same line, but if you had to try and draw a best fit line, everybody's would be different if we just all tried to do it. And you'll learn here this week how this line is come up with, okay? But when the book talks about a linear model, that's what they're talking about. They're talking about the equation that is the equation of the best fit line through the middle, or the best they can through the middle of all those data points. Okay? So understand what that term means. Linear model, it's just a model that represents the data to the best of their abilities. Okay? Then we have a predicted value. Okay? And from the reading, you probably saw that little notation. It's called y hat. Okay? Y hat. Anytime you use a linear model to help you make a prediction, you are finding y hat. That is why back here, when I wrote this equation right here, I used y hat, because this was our linear model. And if I said, well, let's try and predict how many calories a sandwich has that has 32 grams of fat. Well, we could plug 32 in for x and see what we get for y, right? Because remember, x is your fat, y is the amount of calories. So if I wanted to make a prediction, if I knew this sandwich had 32 grams of fat in it and we're going to predict how many calories it has, I could use this linear model to help me make a prediction. That answer I get for y, that's my predicted value. Does it mean the sandwich definitely has that many calories in it? No, it's a predicted value. It's not perfect. Not everything falls exactly onto that line. Okay? So a predicted value, or y hat, is based on the linear model and we use the equation to help us find. Okay? So if you want to get a predicted value, you just use that equation to help you find that predicted value. But the notation I will want you to use is that y with that little Looks like a caret symbol from your calculator above it. Okay, called y hat. Okay? Alright, so let's say here's a scatter plot I have, okay? Let's say that's my best fit line. And I'm going to then, let's say I'm counting by about tens here. Let's say it's about by fives here. I'm just making stuff up here. Alright? If I said use the linear model to help you make a prediction on something whose x value is 24. Well, you come over here to 24, go up, and then come over and see what the y value is, right? Or you can plug 24 into that equation, right? But does that mean that it's going to be exactly right there? No. Probably pretty close if it's got a good r value, right? The r value was good. Well, let's say it only was about right here. Let's say the actual y value was here instead of up here. The difference between the actual value and what the prediction was, that is called the residual. Those of you that read, you remember that word in there a little bit? Okay. The residual is the difference between the observed outcome and the predicted value. The difference between the observed outcome and the predicted value.
Do you like some chocolate?
Yep. Y represents the observed outcome, what the y value actually was, and we know that y hat was the predicted value. Okay? So you just subtract them. Take the actual outcome and subtract the predicted outcome. That is how you can find the residual of a given item. Okay? Oops. We got that? So back here, would my residual be positive or negative? Negative. If I take my observed value and I subtract the predicted value, I'd be taking a smaller number, subtracting a larger number, so I'd get a negative value for the residual. Okay? You know that if you get a negative value for the residual, you know that the observed value ended up underneath the line. If you get a positive value for the residual, you know it actually ended up higher than what the line predicted it would be. Okay? That makes sense? Okay. Those of you that did read, is this helping clarify some of the terms? Yes? No?
Yes.
Okay? 'Cause this gets to be a little tricky. I'm trying to make it as clear as I can. I figured notes might be best today. I apologize for having to listen to me this whole time.
Well, it's all good.
Okay. All right. Now, least squares line. Okay? Least squares line. Yep. The math gets a little bit complicated, and to be honest, Ty and everybody else, I'm not going to worry too much about the math behind it. But I want you to know how they figure it. You're going to be allowed to use your calculator to come up with the equation for the best fit line. You're not going to have to do some of the crazy math behind it, ever by hand. Okay? But I want to explain how that happens. Sometimes, instead of a best fit line, you will see textbooks call it the regression line or the least squares line. Okay? And the least squares line is a good name for it because it tells you exactly how the equation of that line is come up with. And let me try to explain it the best I can. Okay? First of all, the least squares line, we know it as the best fit line. That's all that we've ever talked about. Okay? But in the past, when we've talked about the best fit line, we've been doing the least squares line. Okay? So when I say best fit line, I mean this. It's the same thing. Okay? The reason it's called the least squares line, it is found by finding the smallest sum of all the residuals squared. And there's some very in-depth mathematics in order for you to find the minimum of all those squares added together. Okay? They go through a proof on one of the pages in your textbooks. If you were able to follow along with that, pretty impressive. You're not going to have to be able to do it. Okay? But let me give you a little bit of a picture to give you a little bit better maybe understanding of what I'm talking about here. Okay? Everybody got that definition? Okay. Okay, let's say that's our line of, our least squares line, our line of best fit. Okay? Let's say that is the line that best fits those 4 data points. Okay? This residual right here, okay, that residual, the distance from here to here, would be a positive or negative number?
Negative.
Negative. This one here,
Negative.
negative. This one here,
Positive.
and this one here.
Positive.
Okay? If you just add all of the residuals together, you're probably going to get 0. Okay? Because some will be positive, some will be negative. Okay? But it doesn't really help us out. Okay? Because we're going to get always close to 0 in a sense with ones that are above and below. So what they do is they square each amount. Why would they square every amount? To make them all positive. So they square all those residuals, add them together, and make sure that's the smallest possible sum that you could possibly get. Okay? That's why it's called the least squares line. It's the smallest, that's the least part, okay? The smallest of all the squares added together. There are other lines that you think you could draw that would be in between all those points fairly accurately. Okay? You know, I might have done this instead. Okay? And you know what? You still might, if you would just add all the residuals together there, you might get 0 again. Okay? But I would argue that one doesn't look near as good as the blue one did as far as going through the middle of them. And I would bet you if you add together all of those squares, you would get a number that's larger than what the blue line did when you added together all of those squares. Do you guys follow a little bit where I'm going with it? Do you got any questions? When the calculator gives you that equation on the calculator screen, the line of best fit, it is doing that long mathematical process that they showed you in the textbook of finding the minimum of all those squares, of all those residuals squared, added together. That's why it's called the least squares line. You won't have to do that math, the calculator does it all for you. But I wanted to give you the understanding of what's happening there. Okay? Questions? Thoughts? Anything else right now?
Will the red one be bigger because like there's more positives, like it's as far as it's positives farther away there?
Yep. Because like that value squared is definitely more than the blue one squared there.
Alright.
That one also would be a little bit larger. That one a little bit, the red's a little larger. That one's the red's a little bit larger. But if you would just add together the residuals themselves, you still might have gotten pretty close to 0 on that.
Yeah.
So that's why you can't add the residuals together. You want to add the residuals squared. So that way it gets as close as possible to all of the points. Okay? All right? And then one last term here for you for today. Okay. When the R value shows up on your screen, you also see an R squared value. Okay, you also see an R squared value that shows up. And what that is telling you is it is telling you the fraction, or yes, percentage or decimal, however you want to think of it, the fraction or the percentage of the variability of the Y value that can be attributed to the variation in X. Now put it in terms of context when we get back to that story problem here in just a second. If you don't still have those R and R squared values from the fat and calories on your screen, try and get those pulled back up here a second. What do we have for R squared?
0.961.
0.92.
For R squared?
Oh, yeah.
928 or about 0.93?
0.9.
9228.
Oh, okay, so
92.
9.2. Okay? So, we know that the calories don't fall exactly on our best fit line. It varies a little bit, right? Well, but they're all pretty close. And how I know that is because of this. This is telling me that 92% of the variability in the calories, so 92% of the variability in the calories can be attributed exactly to fat. Is caused essentially by the amount of fat. The other 8%, there are probably different factors causing the variability in the calories. But the way, that's how I would interpret this, okay? 92% of the variability in calories, so 92% of the reason why they vary a little bit can be attributed to how the fat varies in a sandwich. But 8%, some other underlying factors are probably playing an impact on why it varies just a little bit. Okay, so that's how you would describe that in a story problem, and you'll get a chance to do that with your practice. Okay? Yep. Okay? Alright, so a lot of info there today. Your assignment, you can start to do some of these problems. I don't know if you'll be able to do all of them yet. But I got through what I could today. is on page 192. There's a bunch of them.
Oh, yeah.